It's a great privilege for me to introduce uh, today's speaker. Professor Robert Wald is one of the most outstanding theoretical physicists. Right now, he is the Charles Swift Distinguished Professor at the Enrico Fermi Institute at the University of Chicago. Among many honors and awards, last year he won the Dirac Medal as well as the Albert Einstein Medal. And uh, his work spans a diverse arena of physics, classical general relativity, quantum gravity, foundational aspects of time and gravity, uh, gravitational collapse and cosmic censorship hypothesis, black hole entropy as a neither charge, the role or rather status of various conserved quantities in general relativity. Similarly, if you have an embedded rotating black hole in magnetic field, how preferential one kind of charged particles would trickle in and make the rotating black hole charge. So these are many of the exciting predictions that Professor Wald has made. I would not like to hold you between Professor Wald's lecture. So I would request Professor Wald to begin his lecture on black holes decohering quantum entanglement. Professor Wald.
Hey, thank you very much. Right. So, in fact, an alternative good title for this talk is Black Holes Are Watching You, but I don't like to give that as the title because I don't know what kind of audience that might draw. So what I'm going to be telling you about, well, is related to work that I've listed 5 references here. There was some work with a group in Vienna that really got me started thinking about these issues. And the other work has all been done with my now former students, Dane Danielson and Gautam Sadaschandran. Dane is now a postdoc at MIT, and Sadaschandran is now a postdoc at Princeton, but about to move to MIT. So he'll be back together with Dane. The work is mainly based on the 2 papers that I've highlighted in blue, in case people want to dig a little further into the details, a little further than I'd be able to go in this talk. Okay, so what is the talk about? Let's see, my forwarding is not working, so I'll have to do it by mouse. So the talk is going to be about decoherence, and this is very common and in quantum physics, and certainly for people thinking about trying to make quantum computers or things like that, or doing delicate atomic physics or condensed matter experiments that are looking at quantum phenomena. This decoherence is something that has to be dealt with. So if you have a quantum system that is in a pure state, you can't normally completely avoid its interactions with other things that are around, which I'll just refer to as here as an environment. But the environment will respond differently depending on what state the system is in. So if your system that you're interested in is in some superposition state, and the different components of the superposition interact differently with the environment, that will entangle the system with the environment. And of course, the whole system, including the environment, will remain a pure state, at least if the environment was also in a pure state. But the system that you're studying will now be in a mixed state. So that is the decoherence phenomena, and the interference kinds of effects that you would get in a superposition will no longer be present. The two components, if they interact significantly with the environment and the environment states then become orthogonal, then the two components will completely decohere. So what I'm going to talk about in this talk is not the usual environmental decoherence, but the fact that the presence of a black hole will, somewhere near your lab, if it's far away, then the effect will be very small, but provide a fundamental source of decoherence. And the way it works is that the black holes basically, absorb radiation, but this will be very low energy radiation from your system and effectively harvest information from it that way and result in decoherence. And as I'll explain, one can calculate this in a, very simple but still precise and quantitative way. So that's what I'll be telling you about. But to begin with, I want to get everyone thinking in the appropriate direction. I want to begin with a Gedanken experiment in flat space-time. So no black holes here. This is just some ordinary, situation, except that I am going to be concerned with causality and things taking place at space-like separations. So we're very much in the context of special relativity, though not general relativity. So let me take a few minutes to explain this and see if we can get the thinking about this correctly. So we have a skilled experimentalist, Alice, who has a particle. This could be a nanoparticle. It doesn't have to be an elementary particle or anything. But let's say this particle, there are two versions of this experiment, one an electromagnetic one a gravitational one. In the gravitational one, these things have to have mass, but they're going to have that anyway. Let me, though, talk about, since that's much more familiar and easy to talk about, I'm going to talk about the electromagnetic version, in which case this particle, these are two components of a superposition of the particle. This particle has charge, and let me assume it also has spin, so I can separate it into two components with something like a Stern-Gerlach apparatus. Now I'm drawing here a space-time diagram, so forward in time is going upward in the diagram. And I initially started with a particle that has spin in the x direction, but I put it through, so say into the board, into the screen, but I put it into a Z Stern-Gerlach apparatus, so it goes into a 50-50 coherent superposition here. That happened way in the past, so I didn't even depict that. But now, over a time scale TA, Alice brings the components of this superposition back together, with some sort of reversing Stern-Gerlach apparatus. She's very skilled and able to do that. And I'm, of course, assuming there are no environmental effects, so there's no ordinary environmental decoherence. So when she brings this back, one might expect that the if she was careful and the superposition was maintained, then when the components get superposed, the spin will be back in the x direction as it was originally. Okay, but now the twist in this problem is we have some other experimentalist who happens to be named Bob, but is no relation to me, and uh, you'll see why I'm glad about that in the next slide when we see what Bob does when a black hole is present, but no black hole now. And what Bob is going to do is try to figure out which path Alice's particle took. And he's going to do that by measuring the strength of the Coulomb field of Alice's particle. Because if, again, the particle was separated way back in the past, if it went to the right, it's closer to Bob and there'll be a stronger Coulomb field than if it went to the left. So if he releases a particle, it will, from some trap, let's say, at some initial time, it will start moving toward Alice a little bit more and will move toward Alice by the end of this experiment a bit more than if Alice's particle had gone to the left. So, of course, Bob's particle is quantum. He's not going to be able to do a perfect measurement, but again, he'll get some which path information. But the way quantum mechanics works, if Bob has some which path information, well, that really is meaning that Bob's particle is entangled with Alice's superposition, and that means that there must have been at least some decoherence. So when Alice brings her particle back together, there's some chance that the spin will be in the minus x direction when she measures the x spin rather than in the plus x direction. Okay, but now the final twist to this is I'm going to have Alice bring her particle back together and Bob do his measurement of which path. I'm going to have this happen at space-like separations from each other. These are null planes here that I've drawn. And from that, you can see that what Bob does is space-like separated from what Alice does, but that means that, by relativistic causality, whatever Bob does can't influence Alice. So the question is, does Alice's particle maintain coherence or not? Why not? Because Bob can't influence Alice. That's one answer. So yes, that would be that answer. But the other answer is no, she certainly can't maintain perfect coherence because Bob does get some which path information and thereby must be entangled with Alice. So if I were giving this talk to a live audience, I would pause and ask people who haven't read our papers, to give the resolution of this. I should say this is a Gedanken experiment that was originally proposed by Mari, De Palma, and Giovannetti, and it was thinking about this that got us on this whole trail. Okay, so instead of, since I don't know that this would work anyway, instead of asking people to make suggestions, I will tell you the answer. And the answer is that the perfect decoherence cannot be maintained. There will have to be at least as much decoherence as one would expect from Bob's measurement. But Bob has nothing to do with this, as he can't, because he can't causally influence Alice. And in fact, the cause of the decoherence is actually radiation that is emitted by Alice. These paths and the accelerations and so on are different, and there will be different radiation emitted to infinity depending on which path Alice's particle takes. And that causes the decoherence. And indeed, although it may not look like it from what I've said, one can interpret what Bob is doing as simply measuring some of that radiation. So Bob has nothing to do with the decoherence, but he can be interpreted as measuring the radiation that Alice's particle is emitting, which is the cause of the decoherence. Okay, so now the new twist to this is, what if we have a black hole present? And well, Alice is now shown here doing her superposition and recombination, but let's imagine Bob, again, not me, inside a black hole that's somewhere in the vicinity of Alice. I mean, it could be far away, but Bob won't get a lot of which path information then. So, of course, Bob, well, inside a black hole is not a good place to do an experiment, and Bob is going to, in fact, fall into the singularity eventually. But you could have a whole sequence of Bobs, and now the difference between this and the previous experiment is there's no time limitation on doing the measurements inside the black hole, because those are always, by definition, causally disconnected from Alice. That is, things inside the black hole can't, by definition of a black hole, influence Alice. And if you imagine Alice is keeping her superposition open for an arbitrarily long time, then even if there's not that much information to be gathered by a particular Bob doing an experiment before he falls into a black hole, if you have a whole sequence of Bobs, one ought to be able to do, over a long enough time, a perfect measurement of Alice's superposition. Let's say I should have explained that I've drawn here, I should have explained this diagram, so let me take a brief half minute to do so. I've drawn a conformal diagram here, so I've compressed the entire exterior of the black hole region into this diamond here, with null infinity being represented here. So this is really going out to, going out in this direction in null, along a null geodesic, is, going out infinitely far by the time you reach here. I've drawn a black hole that's formed by the gravitational collapse of matter, and I've put Bob and his experiment inside the black hole. Because this is a conformal diagram and I can show infinite amounts of time, I've actually shown Alice's creating the superposition here, holding it open for a very long time. And then this is the part I showed in the previous diagram where she brings the superposition back together. And well, she'll emit some radiation, but I can again have her do this slowly, so there isn't a lot of radiation emitted to infinity. But we'll see that isn't true for the black hole. Okay, so this is just what I've really already said in words, that Bob, or a sequence of Bobs, if Alice holds her superposition open for an extremely long amount of time, can get arbitrarily good which path information, which means Alice's particle has to be decohered. But the punchline on this is that what Bob does, just as in the previous experiment, can't be relevant to Alice's experiment. So it must be the black hole itself that's effectively getting the which path information, and the black hole itself which is decohering Alice and Alice's particle. And that is kind of a little hard to picture how the black hole will do that, one might think, and that's what the remainder of the talk will be about. Okay, so let me go back to the original Gedanken experiment that I talked about in flat space-time and just write down a little bit more with a few relatively simple equations what's going on. So we had Alice bring her particle together and look at the state of the particle when it's brought together. So there's a real problem, a fundamental problem in accounting for degrees of freedom, well, really of the electromagnetic field, in that at finite times where things, well, the particles have not gone all the way out to time-like infinity, and the radiation has not all gone out to null infinity, there's not a clean separation between a Coulomb field, which would be viewed as not having any degrees of freedom of its own, a Coulomb field associated with a particle, and radiation. I mean, you can break up the electromagnetic field that way, but that depends on your choice of time slicing, and it really is not very well defined. I mean, when you go to the Coulomb gauge, you're effectively doing that, but the Coulomb gauge, if you boost your time slice, you get a completely different breakup of the field into radiation and Coulomb. But at asymptotically late times, there is a completely well-defined breakup. The Coulomb field of a particle travels with the particle asymptotically to time-like infinity, and the radiation all goes to null infinity. So if we look at asymptotically late times as to what the state of Alice's system and the radiation is, well, Alice's system will be described by some spin state and some spatial wave function. We've brought the components together so the spatial wave functions are now the same, and this is the spin up and the spin down components that I was showing before in the diagram. But this component is going to be entangled with the radiation that was emitted by the particle following the path associated with the spin up. And this component will be entangled with the radiation corresponding to the spin down. So the point is, if these two states are different, there will be some decoherence between the two. So if there was no radiation emitted and this was vacuum and this was vacuum, then these two things just add up and you'd get the spin X that you started with. But if these two, on the other hand, if these two things were orthogonal, these two components would be completely decohered. So the decoherence is actually determined by how orthogonal these radiation states are. So, and the decoherence that I talked about in the original Gedanken experiment is a result of these states not being the same, and well, they won't typically be anywhere close to completely orthogonal. They'll still have a big vacuum component, but nevertheless, this is not one, and there will be some decoherence. Okay, but now in the black hole case, everything I just said, now doing this Gedanken experiment with a black hole around, everything is the same with one more twist to it, which is the radiation doesn't have to all go to infinity. Some of it can go into the black hole. So the radiation state, in fact, is some state corresponding to radiation at infinity and producted with some state corresponding to radiation that goes in the black hole. Okay, so it's now the orthogonality of this joint state of radiation going to infinity and radiation going into the black hole in path one versus path two. That's going to be responsible for the decoherence. Now, if Alice does everything sufficiently slowly, she can, arbitrarily come arbitrarily close to emitting no radiation to infinity. This state can be arbitrarily close to the vacuum, as would that, in which case they're going to be essentially the same state, and the magnitude of their inner product would be one. So if there weren't a black hole around, she can keep her superposition perfectly coherent. I mean, of course, she has to avoid all other sources of environmental decoherence, but I'm not interested in that in this talk. I'm only interested in the kind of fundamental decoherence due to radiation. But she can avoid that in flat space, and with a black hole around, she can similarly avoid having any decoherence due to radiation from infinity. But what I'm going to show you is she can't avoid having the radiation that goes into the black hole be very small. And in particular, she can't, it doesn't matter how slowly she does the recombination. If she keeps her superposition open for a long enough time, she has no possibility of making this large. And in other words, she has no possible way of avoiding the decoherence of her particle. Okay, so to understand that, we need to understand what's going on with electromagnetic radiation through the horizon. And we need to understand that, well, first at the classical level, and then we need to understand it at the quantum level, of course, to see how much decoherence that results in. So the radiation through the horizon is completely described by, well, what I'm calling the electric field at the horizon. Usually you define the electric field with the field tensor dotted into a time-like vector. I'm defining it by dotting the field tensor into the null normal to the horizon. And this electric field will only have angular components on the horizon. And if this is zero, that is saying that there's no radiation through the horizon. And indeed, if you have, let's just for simplicity consider the field of some static point charge outside the black hole. It's not hard to show that indeed the angular components of the electric field on the horizon will vanish. They really have to. The point charge should not sitting there in a static configuration, should not be radiating through the horizon. But there will be a radial component of the electric field on the horizon, and well, you'd expect that from the Coulomb field of this static charge. And really, this is just saying that the Coulomb field perfectly well penetrates into the black hole, which it does, and that's actually critical. Okay, but now I'm going to consider the very simple situation where we have a point charge initially static, and now I just take that point charge that's located over here outside the black hole, and I move it to some other location, like here, outside the black hole, and then I hold it in this new location forever. So, of course, there'll be some radiation when I uh, move the point charge. Um, and in fact, you can, well, see that from the, divergence of E equals zero, or divergence of F equals zero Maxwell equation, which will tell you in this case that the angular divergence of this angular electric field has to equal the time derivative of this radial electric field. I mean, we have time and R here rather than, radial divergence or something because of the way I've defined the electric field and its radial component with these null vectors. So the radial electric field, of course, is going to change because I've changed the location of the particle, and that implies that the angular components can't be zero. But it implies something much stronger that has the major implications for everything else I'm going to be saying in this talk, which is if I take the time integral of the divergence of the electric field, I'm going to get the difference of the radial fields between the initial and final positions. And those are different. So that's saying that not only is the angular components of the electric field different, non-zero, I'm sorry, while I'm moving the charge, but its integral is non-zero. Its time integral is non-zero. Okay, so what does that have to do with anything, and why am I making a fuss about it? Well, if we were interested in how much energy is radiated into the black hole, that's given by the square of the electric field. And I can make this arbitrarily small by moving the charge slowly. And, in the process, Alice's process, I can completely neglect any radiated energy that goes into the horizon. But what we're really interested in is how many photons are radiated into the horizon. And I'm about to show you that the fact that this is non-zero means that, in fact, an infinite number of photons are going to be radiated into the black hole. If that sounds completely crazy and shocking, I'll give you a little hint that this is exactly the same phenomena as occurs in infrared divergences in quantum field theory when considering scattering phenomena in 4 dimensions. But this is now for the black hole, and actually this would hold in any dimensions with the black hole. So to understand the number of photons, we have to understand what the quantum state of the electromagnetic field is around the black hole, both before and after we perturb it with the point charge. And for a black hole formed by gravitational collapse, the state should be very accurately described by the Unruh vacuum. That is the state that you should get when the black hole has settled down to stationarity, which it would do very quickly. The Unruh vacuum has, the Hawking radiation in it. It's the precise state that would describe what the Hawking radiation would be. Now, it's more convenient to work with the so-called Hartle-Hawking vacuum, which would correspond to a black hole that is in in thermal equilibrium. If you imagine the black hole were put in some box and came to thermal equilibrium with the radiation in the box, that would be the Hartle-Hawking vacuum state at low frequencies near the horizon. These are essentially indistinguishable, so I'm going to work with the Hartle-Hawking vacuum. So when we're interested in the coming with the Hartle-Hawking vacuum is a notion of photons at the horizon. The Hartle-Hawking vacuum is the vacuum of a Fock space of the quantum field. And the notion, if we look at what does a one particle state correspond to, it'll correspond to a solution that's purely positive frequency with respect to affine parameter at the horizon. Okay, so what does that have to do with anything? Well, each component of Alice's particle is going to radiate into the black hole is at the quantum level a coherent state associated with the classical retarded solution associated with the charge current source provided by each component of Alice's particle. So that gives rise to the following formula for the number of photons that a given component of Alice's particle will radiate into the horizon. Or we can forget about Alice and go back to my point charge example. And what this is saying is if I want to know how many photons are radiated into the horizon when I move the point charge from here to over there and leave it there forever, I calculate the vector potential at the horizon associated with this by looking at the retarded solution. I Fourier transform it on the horizon. I take its positive frequency part. That's why I'm integrating only from 0 to infinity. I take its positive frequency part with respect to affine parameter on the horizon. And then I take this integral, which would be, I think, to many people or people who've studied Klein-Gordon quantum field theory, easily recognizable as the Klein-Gordon norm of this mode function. This extra omega factor comes in the integral of the amplitude squared in Fourier space of the radiation. So this is the number of photons that gets radiated into the horizon. But now we have a situation where the integral of the electric field is not, the angular components of the electric field is non-zero. That means that if we integrate this, the vector potential has a step function kind of behavior, the angular component. So I think I have a diagram on the next slide, so let me jump ahead to that if I can. Yeah. So this is what the vector potential must look like in this process where, let's say, I take a point charge that initially was here, and by gauge, I can assume the vector potential is 0. The angular components of the vector potential are 0 here. In the process of moving it, the angular components will be non-zero, but when I leave it in its final position, the radiation will be 0. There'll be no time derivative of this. So the electric field will go back to zero, but the vector potential won't go back to zero. But the instructions for calculating the number of photons are to Fourier transform this. When I Fourier transform this, I'm going to get a 1 over omega divergence. That's just what you get with a Fourier transform of any step function that, with a non-zero step. So let me jump back to my previous slide. This is the integral that we're supposed to take, but this Fourier transform diverges like 1 over omega. I have to square that. That gets multiplied by omega. If I was doing energy, that would get multiplied by omega squared, and I'd get a perfectly finite integral that I could make very small. But with only 1 power of omega here, I get a logarithmic divergence. And so if I did my point charge experiment, held it here, moved it over here, and held it there forever, I will radiate an infinite number of photons into the black hole. And as I've already said, this is exactly what happens when you do scattering theory calculations and calculate the photon radiation. There, it's a change in momentum that results in this kind of infrared divergence. Here, it's a change in position that will result in this kind of infrared divergence. Okay, so well, we're going to get back to Alice's experiment and see how much decoherence there is, but it will be important for making estimates to see if I have this point charge example, how large this step is in the vector potential between its initial value and its final value. And that can easily be estimated from Coulomb's law. If your point charge is some distance b away from the horizon, the radial electric field will be roughly charge of the particle over distance squared. That is just Coulomb's law. The change in electric field caused by moving in radial electric field caused by moving the charge a tiny little distance d will be given by this sort of dipole formula. And when you go through how much of a change in the vector potential that corresponds to, well, you have this dipole and distance cubed coming in from here, and then there's a factor of m squared that you'll also get from the volume element that comes in the Klein-Gordon inner product, given that the radius of the horizon is of order n. Okay, so now let's go back to Alice's experiment and see how much decoherence there is. And the point, each component of Alice's particle is like this point charge that gets moved, held in position, but it's not held in that position forever. It's moved back to its original position. That's what happens when Alice is closing her superposition. So each particle is, each component of her superposition is doing that. And that gives rise to this, well, if her superposition was held open forever, that would give that logarithmic divergence, and I'd get infinity here. But if she's only holding the superposition open for an affine time v, there'll be a logarithmic term log of v coming in here. Now, if the effect were just logarithmic in time, that you really have to wait a long time for there to be a big effect. But there is an exponential relation between affine time at the horizon and time in Alice's lab. So this logarithmic effect actually turns into a linear in time effect. So what I'm saying is that in Alice's experiment, this is how many photons she will necessarily, I mean, she could emit a lot more than this by doing her experiments sloppily, but no matter how carefully she does it, the infrared photons that are going to go into the black hole will, in number, correspond to this that linearly grows with time. Now, by the time that more than one photon has been emitted, the two states that you get will be orthogonal or nearly orthogonal, and complete decoherence will occur. So we're now ready to give the answer to Alice's experiment. So now in her experiment, she's put her particle in this spatial superposition. She keeps the particle superposed for a time capital T, and then recombines the particle. And what's relevant is this number of what you might call entangling soft photons that controls the orthogonality of the two radiation states. By the time this is bigger than one, will have complete decoherence. So if you turn around the formula, it says that if Alice holds her superposition open for a time equal to the sixth power of her distance from the black hole, the third power of the mass of the black hole, and the kind of effective dipole moment she's created with this superposition squared. These are all in units where G, C, and H bar are equal to 1. By this time, if she waits this long, her particle will be completely decohered due to the black hole. So I've written this in units where G, H bar, and C are 1. That might be useful to convert this back to more normal units, and might be useful to see what the size of this effect is in an example. And I've given an example here, and all the experimentalists can breathe a sigh of relief that they don't have to worry about this effect in their own laboratories, because the example I've given is, suppose that our sun were a black hole and Alice's lab was at a distance of this black hole that the Earth is from the sun, so that's really quite far away from the black hole. And suppose that she had her superposition was actually made out of an electron. I mean, you do better with a nanoparticle, but let's imagine that it was an electron and she separated it by a meter. That's pretty generous and not that easy to maintain a superposition of that sort, but let's suppose she did it. Then the black hole at the position of the sun would decohere her superposition in a mere 10 to the 43 years. Okay, but if you were really close to the black hole, say corresponding to at a distance corresponding to last stable circular orbit, that's awfully close, then you're really talking at same other parameters, then this would be a decoherence time that would only last 5 minutes. So this particle would be decohered in only 5 minutes. Again, separating an electron by a meter for 5 minutes in anyone's lab would be a very, very tall order due to all the other environmental effects. Okay, so I've been talking about the electromagnetic case. I think let me just very briefly mention the differences. There's one major subtle difference in the gravitational case. Otherwise, everything really works in amazingly good parallel. So let's say that Alice does her experiment just with massive particles. She can't really avoid doing that anyway. And Bob is going to, well, in the original experiment, Bob is going to measure the Newtonian-like gravitational effects to get which path information. That would be the analog of measuring the Coulomb field that I was talking about in the original experiment. Okay, well, the analysis, and now we want to do the black hole version of that. The analysis follows by incredibly close parallel, where one uses the electric components of the Wald tensor rather than the electric field, and compares that with the radial component of the Wald tensor instead of the radial component of the electric field. And instead of using the divergence of electric field equals zero equation as in electromagnetism, which is the constraint equation that you have in electromagnetic theory, we use the Bianchi identities in the gravitational case, and the Bianchi identities on the Wald tensor, when the vacuum field equations hold, are given by these formulas here. And if you put it together, you have the same equation you had in the electromagnetic case, except you have two indices, and you have a double divergence, and you have a second time derivative coming in. But you also have a second time derivative coming in the relation between the Wald tensor and the metric perturbation. And the upshot is that you have exactly the same, well, memory effect. I think I didn't use that term. I should have, but the fact that the vector potential doesn't go back to its original value is precisely corresponds to what is called the memory effect at null infinity. And so you're getting exactly the same sort of memory effect on the horizon of the black hole. And in the gravitational case, this corresponding effect is called a memory effect. There is one difference that occurs in the gravitational case, which is that you might think that Bob could measure the difference in Newtonian fields, that would also be a dipole effect. But in the gravitational case, there is an effective conservation of center of mass law, which implies that if Alice creates a little dipole with her particles, her lab will actually move in such a way as to cancel that dipole. In a sense, this is exactly the reason why gravitational radiation starts at quadrupole rather than dipole in the non-relativistic motion kind of case. So what turns out to be relevant is the effective mass quadrupole that's produced by her superposition. Otherwise, if you carry things through in complete parallel, you get this formula for the amount of time it would take to decohere Alice's superposition. So you have a higher power of the distance from the black hole, which is really coming from this quadrupole rather than dipole effect. And you have this effective quadrupole squared here instead of effective dipole, and you have a correspondingly higher power of mass of the black hole. If you put in the estimates for what this is, well, in my example here, you get a decoherence time of 10 microseconds. That is really fast. And, that is making it sound like this gravitational effect is big. But this is the decoherence time. Again, if our sun were a black hole and we were a distance from the black hole that the Earth is from the sun. But now I'm doing the example of you take the entire Earth and put it in a superposition with itself, separated by an Earth radius. So that is, to say the least, a rather tall experimental order. But if you could manage to put the Earth in a coherent superposition with itself, separated by an Earth radius, and the sun were a black hole, it would decohere that superposition in just 10 microseconds. But for anything realistic, the decoherence time is way longer than in the electromagnetic case. Okay, a final comment that I want to make is that really the only thing that was used about having a black hole is having a killing horizon present. And that means that everything I've said in the talk having to do with black holes can be immediately generalized to an accelerating lab, and where you have this Rindler horizon. If you have a uniformly accelerating lab, again, spatial superpositions will decohere with formulas that are direct analogs of what I derived. And in the case of de Sitter spacetime, where you have a cosmological horizon that's a killing horizon, again, the same analysis occurs. So in the de Sitter case, in the electromagnetic case, you get a decoherence time equal to the cube of the Hubble radius divided by the dipole squared, again in units where G, C, and H bar are 1. Well, the G isn't relevant for this formula, but the H bar and C are 1. And again, in the gravitational case, you get a higher power of the effective distance to the killing horizon, and you get the quadrupole coming in squared rather than the dipole squared. Okay, so what have I told you? I mean, just to wrap up and conclude. So what I've shown here or attempted to show in this talk is that black holes, and as I just said, much more generally, killing horizons, manage to harvest information about quantum superpositions of spatially separated components. So that's what I meant in my subtitle at the very beginning of Black Holes Are Watching You. They are gathering information about your quantum superpositions and figuring out which path your particle is actually in effectively. The mechanism by which they do this is absorbing radiation, but the relevant radiation and the thing that you can't do anything about is this soft radiation, the same type of phenomena associated with infrared divergences. So the long range fields penetrate into the black hole and they change the state of the field, on the horizon, in this kind of soft graviton or soft photon manner. And that's how the black holes get the information about your superposition. And if you wait long enough, even though you're not doing anything and you're just holding your superposition open, the black hole will harvest enough information to decohere your superposition. So I think I've also illustrated with my numerical examples that this is certainly not going to be of any practical importance for any experiment that anyone might even contemplate trying to do. But I think it may be giving us hints of some significance for our understanding of the nature of black holes and quantum gravity. Okay, so thank you very much.
Thank you very much, Professor Wald. So now the session is open for a few questions. Possibly I will kickstart the question session. So that was a very exciting talk. Now, is an analog whether this calculations can be done for acoustic black holes, where because of finite velocity of sound, you have an effective horizon. So many of the conclusions that you have, can it be tested in acoustic black holes in the lab?
Yeah, actually, I haven't thought of that, but certainly off the top of my head, everything, including, the kind of radiation and so on, would in principle, apply to the acoustic black holes. But I mean, the trouble is the models and certainly the kinds of things you could do in the lab are typically only good models of the black hole in some limited frequency range. I mean, obviously any of the condensed matter things certainly wouldn't be very good at very high frequencies. That's no problem because the high frequencies are not relevant here. But they would have to be a very good model of the black hole at extremely low frequencies as well. So I think one would have to look at things on a case-by-case basis to see that we're talking about radiation that is extremely low frequency, and it's really, and I guess we really need an analog of a Coulomb field or Newtonian field of the thing that we're putting into superposition, and something of that sort that would go through the black hole horizon. So, I mean, in principle, if one had like Bill Unruh's original, model was sound waves in a fluid. If you just had a fluid with the sound waves and everything worked at all frequencies and so on. And I guess you also need, when you're making the superposition, that there's some analog of a Coulomb field that might be an issue with the sound waves. But anyway, that almost everything and possibly everything would carry over. But, the fluid, a laboratory fluid is not going to behave like the fluids in the model is probably not going to behave that way at incredibly low frequencies. And of course, probably even the more major showstopper in terms of some experimental verification of this is, I've assumed that there is absolutely no environmental decoherence from other causes. But in these condensed matter models, I mean, avoiding environmental decoherence and then seeing this really subtle, very low frequency effect, I think is probably not going to end up, being close to something feasible to do. But that would be interesting to think about further and see what elements would in principle work.
Thank you, Professor Wald. Professor Panchapakeshan has a question.
Yeah.
Yeah, Professor
Hello,
Panchapakeshan.
by the way. Oh, you're muted.
I think Professor Panchapakeshan, you're muted. Professor Panchapakeshan, you must unmute.
Okay, I just wanted to ask whether these arguments have any relevance for the information loss when Hawking radiation makes the black hole disappear.
Yeah, not really. I mean, if anything, they make the information loss issue, more difficult to overcome, because now one can see that there's a lot of, soft information that the black hole absorbs as well. But I mean, one might be tempted to think that this might help because the Hawking Perry Strominger ideas were somehow related to soft radiation and soft hair they talked about. But in what we're talking about, there's no sort of soft hair on the black hole that you can go to later and pick up the information about what went in. Everything is really going into the black hole. So if anything, it's making the information problem worse. But, if you can solve the information problem, before what we said, this will only add an extra complication. But I don't see that this helps provide a solution in any way.
Thank you.
So Professor Rao has asked a question. Let me read out the question. So the question says, the spin degree of freedom has nothing to do with charge and does not reside in 3D space. Thus, what Alice does with Stern-Gerlach in Z direction on an initial X state and then takes it away should not affect any Coulomb effect of that particle on Bob.
Okay, so
yeah.
Okay, so I had spin. Let me see if I can get back. Yeah. I gave Alice's particle spin, and I assume that just in order, the spin is playing absolutely no role in this. But with the spin, I have an sort of straightforward mechanism for separating things into a spatial superposition with a Stern-Gerlach apparatus. But more importantly, it's a very clean situation when I bring the particles back together. I can just ask, does the spin go back to the x direction, or is there some possibility that it might be in the minus x direction? And that's a clear criteria for whether there's no decoherence or some decoherence. I could just as well not have the spin separated into these superpositions and then do some kind of interference experiment and see whether I get a wiggly pattern on the screen or the non-wiggly pattern that you'd get if these were decohered. I wanted to avoid doing that because there are previous papers in the literature doing talking and not talking specifically about this Gedanken experiment, but that make some arguments about not there being some Planck scale limits, or Planck length limits, imposed on the interference pattern due to quantum gravity effects and so on. And so I wanted to avoid having to do an interference experiment. And if we do the spins, we can avoid that cleanly. But otherwise, the spins are playing no essential role here. So I'm not sure if that fully answered the question, but the spins are completely inessential in this discussion. We just have to work harder to figure out how to make the superposition and work harder to figure out if it remained coherent.
Just to add a comment, since every particle has mass, one can just take the gravitational waves going into the horizon of the black hole and check the decoherence.
Well, the particles that we're talking about, I mean, in Alice's experiment with the black hole, the particles are never going into the black hole. It's only the gravitational radiation that goes into the black hole. The gravitational radiation due to the particles traveling these different paths.
And circumvents having charged particle, since everything has a mass, even superposition of just normal magnetic moments without any charge, but the gravitational waves going in would cause the decoherence.
Yeah, everything will in fact decohere, but if I mean, even interaction, even massive fields, will have some radiation going into the black hole. They'll just be much smaller. I mean, so, if we did this with magnetic moments or something instead of charges, and again neglected the mass, we'd still get some electromagnetic effect. It would just be much smaller, and now we'd have to be looking at the difference of the radiation from the different magnetic dipole moments. But everything will have mass, so in the gravitational case, the analysis that I described would apply to everything. But in the electromagnetic case, I mean, we could do this with neutrons and there still would be an effect because they have a magnetic dipole moment, and they would radiate differently, but it would just be a very tiny effect compared to what you'd get with charge. But the linearly growing in time would apply to everything.
Thank you. I think there's the last question from Professor Hegde. He asks, if black hole can decohere any quantum superposition, is there any rate at which it decoheres, or does it depend on any other factors?
Yeah,
Sorry,
well,
Professor, I apologize, folks. Professor Patrick Dasgupta, Arnav has been asking questions. He was, in fact, first in queue. So maybe if you could, his question could also be taken up, please.
Sure. Yeah, absolutely. Yeah, after this question. Yeah.
Thank you.
Okay, sorry. The question was, what is the rate of decoherence? Well, I gave a decoherence time here. This is the time at which nearly complete decoherence would occur, but it is the deco the well, okay, the decoherence rate, is exactly what's given by this, what, 1 over this decoherence time is essentially giving you the decoherence rate. So this is in the electromagnetic case, and the corresponding formula in the gravitational case is this. So if you just take 1 over this, that would be the decoherence rate.
All right, thank you. Question by Mr. Arnab Barbad. It says that in one of the slides, it was assumed in the calculation that superposition stays forever. What if experimenter opens a special superposition, then recombines them before any soft particles can reach any horizon?
Well, I mean, right, when, this is the vector potential that's associated with creating the superposition and bringing the superposition back to zero. So if we hold it open for a very long amount of time, the frequencies will be 1 over the time we're doing it. I mean, I should really distinguish, between the affine time and the killing time or the proper time in Alice's lab, but the idea is still basically the same. So, there isn't an infrared divergence in the actual experiment because we're bringing this back to zero, but 1 over the time, that I'm keeping it open is the important frequency that comes in, in creating this this infrared divergence. So if we do the superposition very quickly, then we're not going to. I mean, it's not a question of how quickly we bring it back together and how quickly we open it. It's how long we leave it open that is what's most relevant. If we don't leave it open for a long time, then we don't get a big effect in this manner, though, of course, we'll still get some radiation from the opening and the closing, and we'll still get a little bit of decoherence, but that can be way smaller than what I was calculating here. if that, so I think that was addressing the question, but
The second question that Arnav asks is, does it mean no long-term quantum computer would ever be stable because of this decoherence?
oh yeah, but we're talking, I mean, yes, but I don't know that anyone is thinking about a quantum computer that's stable for 10 to the 43 years. And this is, we don't actually have any black hole as close to us as the sun. And we don't have to do something as challenging in a quantum computer as keeping an electron in a spatial superposition separated by a meter. So, you know, you can do way better than the 10 to the 43 years due to this effect. And again, I don't think anyone building a quantum computer is looking for it to work coherently on that sort of time scale.
Thank you. So all the questioners have also thanked you in the chat box. Are there any more questions? Well, there doesn't seem to be any other question. So wonderful. I really thank you, Professor Wald, to have delivered such an exciting lecture, and it has raised a lot of questions. And on behalf of everyone, I thank you very much.
Yeah, okay. Well, I enjoyed being here, and thank you.